Okay, welcome to Chapter 8, Rotational Kinematics. Also, it can be seen as linear kinematics. It's the same concept from earlier this year. It's just the changing of variables. So for Section 8.1, we're going to be looking at rotational motion and angular displacement. Angular displacement can be viewed as the x linear kinematics, but it's mostly referred to as theta. So for rotational motion, it's the center of all circular paths that define a line. It's called the axis of rotation. Basically, which means that the angle through which an object rotates about a fixed angle, which is also called the angular displacement, theta. So if a rotating object can be positive or negative, it has to depend on whether or not it's clockwise or counterclockwise. Since we're looking at rotating objects, you're going to have to see which direction it's pointing, and it will tell you based on that whether or not your answer will be positive or negative. Okay, so angular displacement can be seen in 3 different units, and most of the time you're going to have to convert from either degrees, which is 360 degrees, 1 revolution, which is 1 complete turn, and radian, which is theta. So if they originally give you a problem of revolutions, you're going to have to keep in mind that you have to convert to be able to get into radians as your final answer if they're asking for your final answer in radians. So theta equals arc length over radius, which is S over R. So to go furthermore, it would be 2 pi r over r. The r's would cancel out, and it would be 2 pi radian. So 2 pi radian would equal 1 revolution. And if you want to get from radians to degrees, you would have to use the degree. So if there's 360 degrees and you already know 2 pi radian equals 1 revolution, you can divide both of those and get 57.3, which equals 1 radian. So throughout this whole time, you're going to just have to keep in mind that it's basically the x in linear kinematics. So let's look at a rotating problem. If the disk rotates all the points along the radial line, then it will experience the same angular displacement, theta. So just because the theta is constant through all points, it's seen in figures 8.2 and figures 8.3, it doesn't necessarily mean that the sides are all going to be the same. So it's not a constant arc length. So you just have to look at it and based on that. So throughout this whole thing, you have to know that just because the theta is the same, just how inside 1 is smaller than side 2, doesn't mean that the arc length is going to be the same. And below for you guys, I wrote how to know how to find sides, how to find theta, and I'm just showing theta equals side over r, or side equals theta times radius. Now let's check our understandings. If 3 objects are visible in the night sky and they have the following diameters, 4d, 2 theta, 3d, theta over 2, d over 2, theta over 8. They want us to rank it in descending order according to a distance from the observer. So like I said before, theta equals S over R, or diameter over distance, and you just have to look at their diameter, which for A would be 4, for B would be 3, and for C would be 1/2. You're dividing it over their distance, which is their angle, so you're going to have to divide it by A for 2, B for 1/2, and C for 1/8. So based on that, you just get whole numbers 2, 6, 4, and just based on that, you would get BCA. Okay, now let's look at a real-life problem. If a pitcher throws a curved ball that reaches the catcher in 0.6 seconds, and the ball curves because it's spinning at an average angular velocity of 330 revolutions per minute, there's one of the units, revolutions per minute. On the way to the catcher's mitt, what is the angular displacement of the baseball in radians as it travels from the pitcher to the catcher? So you see there that they're asking for a different unit at the end. So we have to just lay out all the things. So if time is going to give you 0.6 seconds, the angular velocity, which is seen as W, would give you 330 revolutions per minute, and they're asking for theta, the angular displacement, in radians. So not only are we going to have to find theta, but we're also going to have to convert. So velocity equals distance over time, so the same thing could be said for angular velocity, which would give you theta over time. And we already know our velocity, but we only know it in revolutions, so we have to convert. So if it's 330 revolutions per minute and we want to get it into radians per second, we're going to have to use 2 pi radian, which gives you 1 revolution. And remember, pi is not a unit. You actually have to plug in 3.14 into your calculator. So you multiply that, and you also have to give 60 seconds equals 1 minute, and you would get 34.56 radians per second. So that's your angular velocity in radian form. So you're going to put that in for your W, and you're just looking for theta. You already know your time, so you're just multiplying each, and your theta would give you 20.73 radians. Now let's look at the last problem. Our sun rotates in a circular orbit about the center of the Milky Way galaxy. The radius of the orbit is 2.2 times 10 to the 20th meters, and the angular speed of the sun is 1.1 times 10 to the negative 15 radians per second. How long in years does it take for the sun to make one revolution around the center? So they're giving us one revolution, and they're giving us radians per second, and they're also giving us meters. So one of them's linear, another one's angular, and it's another form of angular, but in revolution. So just lay everything out. Radian's going to give you 2.2, angular velocity is going to give you 1.1, and since it says one revolution, we already know from that it's 2 pi. So you have to keep that in mind when you're looking at it, that it won't flat out tell you 2 pi. You have to base off one revolution. And they're asking for time. So we can find our tangential velocity. The tangential velocity formula can be seen in your formula sheet. And it also could be seen as linear, so you can use the radians there because it's in meters, and it will cross out. Well, it will actually be used, not cross out. And so if tangential velocity is radian times angular velocity, and you have those both, you can multiply them, and you'd find your tangential velocity as 264,000 meters per second. And you can also use circumference, and you can know that since you already have your radian, you can use 2 pi times the radian and get your overall distance, or your diameter, of your whole circumference, which would be 1.38 times 10 to the 21st meters. So if we already knew, like before, velocity is distance over time, we can use the same thing. We can use the tangential velocity as v. We already know our distance because of the circumference, and we're just looking for time. So everything will end up canceling out, and we would just do 1.38 times 10 to the 21st over 264,000, and it would give you 166,032,082 years. So throughout all Chapter 8, you're just basically going to realize that it's the same thing as linear kinematics, just an add-on with concept questions, but that x will be theta, w will equal v, and alpha will equal a. And that's 8.1.